Okay, so welcome back after one reading week. Before we proceed to the continuation of the material, there is some info regarding the second midterm. As you know, it's on Tuesday, March the 3rd. It's 75 minutes as usual. For each student, the precise time and location can be found at the link that you used last time. So, well, it's given here, so you would have to put your info, etc. Yeah, you have a given assigned location. There were two people who actually showed up at the wrong classroom, so be careful on that. If you have a class conflict or something like that, you have some possible alternate rights, either before the midterm or in the morning of the following day. This is the whole reason I'm doing this announcement, because the deadline to do a request for a testing on alternate writing, if you have a conflict, is no later than noon on Wednesday, February 26th. So that is the deadline. Please keep it in mind if you actually have an issue. So this is the most important part of the announcement, I guess. The format is the same, 15 multiple choice questions. We start from section 5.2 and we end over 7.1. Of course, if you notice, the course is constructed by developing derivatives and integration. So of course you need to understand the material from previous sections in order to do that, but this is the coverage for the second midterm. You have sample tests that you can check. Of course, the requirement, HB Pencil, student ID. You already know the standard calculators that can be used. And there are two review sessions on Friday, which are in this location. So most probably you have seen all this information during the reading week. Just keep in mind the deadline. I think that's the important part. But in any case, we'll continue with a new topic. Actually, Professor Kang covered me in the last class, and the material that he studied was improper integrals, so he pretty much finished the material. We are at the same stage as he is in his course, so he's one of the three instructors. We'll continue with the course coordinator. And so we start a new topic, which is 7.1, which is the last topic of the midterm, if you notice. So it's functions of several variables. So you may or may not have seen this before. If you haven't, we will do an introduction. If you have a function that we're going to call f of two independent variables, we're going to call x and y. So as any function, right? What you have is a rule. So it's a rule that assigns to each pair, ordered pair because you write always the x before the y, ordered pair, xy, in a given set D, which is the domain, exactly one real number, which we're going to denote by f of xy. So f of xy is the rule, right? We have a pair, xy, we have an association. So, well, at this point, if you think about that 1D functions, such as the log, the domain is defined or limited by the region in the real line where that function is valid. And in the case of 2D, is the same. Usually, the domain will be the region in which it kind of makes sense or you can apply the function. So just to give an explanation, because that will come up in one of the exercises, we usually assume the domain of f is the set of all points xy for which f of xy is defined. And Well, the extension is natural, right? I mean, the same way we went from functions of one variable to two variables, we can define functions of three variables, four variables, as much as we need. So we can also define functions of three independent variables, such as f of xyc, and also four independent variables, such as f of x, y, c, t, etc. And in fact, if you think about it, you live in a 4D space, right? The space, as in the space in this room, is 3D. But you have the time as well, so that is your fourth variable. So you're quite familiar actually with a 4D space such as this one. And in classical mechanics, you also study that kind of space. In relativity, you also have something like that. So I'm just trying to build up into some intuition where this is not new for you. You actually have some understanding of that. And the T stands for the time. So the first exercise or example is to introduce a given function which is of the form f of xy equal to 3x squared plus 5y divided by x minus y. So the first question of the exercise is to find the domain of f. I will do the exercise, but first I want to ask you, which is why I took my time of explaining all these concepts of the domain and everything else. What is the domain of this function? Where do you have an issue when you want to apply this function? Well, the denominator would be a possible issue, right? What is the problem with the denominator? In which points might I have an issue? Sure. Right, exactly, right? When x equals y, x minus y is 0, the denominator is 0, so that is one possible issue. So clearly, the line y equal to x cannot be part of the domain. So basically, f of xy, is there a question? I really mean it, like, is there a question? Or is it blurry? Like, can you guys see or not? Okay. It's defined for all points except for xy such that x minus y equals 0, right? So the domain is the set of all points in the xy plane except for the line y equal x. So, okay, that is one. If you have not seen functions of several variables, this is important because the points where the function is not applicable can be a little bit more complicated. So the second is to compute f of 1 minus 2. And here it's just to learn how to manipulate the objects, right? So it's 3x squared, so this is 1 squared if you want, plus 5 times y, which is minus 2, and then 1 minus, well, x minus y, so you have minus 2. So you have 3 minus 10, and then 1 plus 2, so minus 7 divided by 3. So, sorry if it becomes a little bit blurrier than usual. I changed to the squared sheets. In fact, for graphs, this might be more useful than the previous one. You have more info, but if it becomes blurry frequently, just let me know, okay? So, okay, after this exercise, we will do a new one, which is to consider the function f of xy x times e to the y plus natural log of x. So the first indication is to find the domain of f. So, okay, before I do it, you have this function, right? It's a combination of the product of an exponential and x and then natural log of x. Where are you going to have issues with this function? And this is a 1D case, right? At least, well, just wait. This one doesn't have an issue. E to the y can be defined for all y, likewise for dx. Your issue will be with natural log of x. It's actually not involving y in this case, that's why I was saying that it's like a 1D problem. But of course, you know that for the log, you cannot define in the real numbers a natural log such that x is less or equal to 0. So x times e to the y is defined for all xy, but natural log of x is defined only for x greater than 0. That you know from the previous chapters. So the domain of f is all pairs xy such that x is greater than 0. Right? So basically you will have half of the plane. The second question is about a computation. So it's to apply the function at the point e squared natural log of 2, and you just have to plug in. So x is equal to e squared if you remember the rule, which I guess you can see from here. So you have e squared and then e to the y, which is natural log of 2, plus natural log of e squared. So far so good, right? We just basically manipulated. So this is e squared times e natural log of 2 is 2, so this is multiplying, plus the log and exponential are inverse functions, so you get 2, and you can factorize this as 2 times e squared plus 1. Okay? So the examples are chosen so that you get familiar with how to compute functions in several variables. You have a rule. Of course, there is an order in the pair x and y, first x, then y. Given the values of the point xy, which is e squared, comma natural log of 2, you do the application of the rule by f, and you compute the result. It's just to get you familiar with that. It's nothing else. The third example. So is there any question at this point? Or so far so good? Yeah? Okay. So in example 7.1.3, given the function of 3 variables, so again, in this room you have x, y, and z. X, y could be a plane, and then the z is the vertical component who make you see that you're familiar with this kind of space. The rule is of the form xy plus xc plus yc, and you have to evaluate, sorry for a messy thing, f of minus 1, comma 2, comma 5. So this is what you have to compute. So if you do the computation, it's basically use this rule. So f of minus 1, comma 2, comma 5. So x is equal to minus 1, y is equal to 2, plus xc, x is minus 1, c is equal to 5, plus y is equal to 2, c is equal to 5. Okay? So if you do the computation, this is minus 2, minus 5, plus 10, 10 minus 7, you have 3. Again, it's to make you familiar. Actually, this function is quite well behaved. It's basically products of x and y, or x and c, etc. So you won't have any issue into defining this function in the 3D space, which is why the question of what is the domain was not being done for this one. But you have to become familiar into how to manipulate these functions. So, are there any questions at this point? Can I continue? Okay. So far we have done the introduction of the function of several variables, and we come to a part where we have to do some application problems, which you might find interesting. And, well, the first application problem is to see why this might be useful in a revenue computation. So if you go to exercise 7.1.4, have the revenue as a function of two variables. So, statement of the problem in the textbook is a little bit long, so I will just give the important information. Basically, you have a sports store, and you have two brands of tennis rackets. So the first one is the Williams brand, because of Serena Williams. So it sells for X dollars per racket. So what you're doing at this point is basically defining the functions of interest or the variables of interest in your problem, because later on you will define the function based on those variables. The second is because of Maria Sharapova, so Sharapova's brand, which sells for Y dollars per unit or per racket. So this is the racket price. And in order to calculate the revenue, you also have to introduce the demand. So we'll just quickly write the demand for the Williams brand, which we're going to call V1, is equal to 300 minus 20x plus 30y. Now, I'll finish and I'll make an observation. It's per year. So if you notice, the demand for a particular brand depends not only in its respective brand, which would be the Williams, but also in the other. So that's the new thing about the problem, right? Basically, okay, you are a seller, you have two products. How much they demand, basically, in a way, these are in competition with each other, and the amount for which each racket is sold affects the demand on the other. So just to be mindful, this is why you have a function of two variables. In the case of the other competitor, which is the Sharapovas, so you have a function D2, which is equal to 200 plus 40x minus 10y, and it's rackets per year. So this is the function D2. Again, it's on the two variables, so which is the unit price or the racket price. And the indication of the exercise is that you have to express the store's total annual revenue. So keep this in mind. From selling these rackets as a function of the prices, which are X and Y. Okay. So, well, you basically just have to do the same computation that you do when you go to a store. How many units you buy from each product, and what is the price unitary? It will be the same for these two. So this is, of course, related only about these two brands. So I'm pretty sure that if I write a single equation, it will be clear. So this is a calculation of the revenue, because we're actually caring about the annual revenue. By the way, there is a typo in your textbook. If you look at the solution of the exercise, it's indicated something like total monthly revenue in the solution, so just keep it in mind. But okay, the revenue according to these rackets, okay, is the price of the first racket times the demand that you have in a year plus the price of the other racket plus the demand. And of course, we're considering the span of a time of 1 year. So that's why we'll go from the units to the revenue. So we'll just substitute. So this is x times v1, which is 300 minus 20x plus 30y plus y, which is d2, 200 plus 40x minus 10y. So we have 300x minus 20x squared plus 30xy plus 200y plus 40xy minus 10y squared. So in terms of the polynomial, the only ones that can be combined are these two. So you have 300x plus 200y if you want to order in terms of the degree of the polynomial. Then you have 70xy, so you are counting for this sum. Then you have minus 20x squared minus 10y squared. So you go from the linear to the quadratic terms. First x and then y, and this would be the result. Okay, so this would be the way that you will handle the computation. Regardless of the nature of the problem, either business. So can everybody see up to this point? Okay. So look, functions of several variables appear not only in business, of course in physics and so on, as you can see from the space and time computations. Also, if you think about it, whenever we dealt with these problems of compound interest, we had many parameters that we assumed that were constant, such as the annual rate, etc., etc. But formally speaking, you can be more abstract and think of those as possible parameters that can be changed and not have only a constant value. So actually part of the issue will be that when we consider functions of several variables, we will consider some of the previous models, but allowing some values that we assume constant to change. So, yeah, I mean, having a function of a single variable would be really lucky, right? I mean, because essentially what you would assume is that you have a phenomena where things only depend on one single thing. And that is very rarely the case. It can be due to the dimensionality of the problem. Many times things can be studied in 1D, but that cannot be always the case. So the second model will be related to output at the factory. This might be interesting, actually. So the output, which we're going to call Q at a factory, so this is going to be a function of the amount K of capital investment and the size L of the labor force. So, have you guys seen something related to this on your own courses, like not math related? Perhaps? I'm not a business major, but I'm curious if we go at the same rate of your courses or ahead or before. So there is a model which is called the Cobb-Douglas production function, or maybe a family of models. That's why we will say it in plural. So which is Q of K and L, which is of the form A times K to the alpha times L to the beta power. So if you want to see the relation, basically this is the output. This is a constant parameter. This is the capital investment amount, of course, to the power alpha. There is one comment about the power, so wait for me 1 second. So L is the labor force size. So I just want to show how in this model, where functions of several variables are assumed, how they interplay, right? So there is actually, okay, this value is constant and the alpha and the beta powers are constant, but there is a constraint. So there is a constraint for, so I mean, okay, alpha, beta, constant too. Okay, that's, and also A, that's fine. But the constraint that happens between the powers is that alpha plus beta must be equal to 1. That is by assumption, okay? You will see later in one of the examples why that is taken as an assumption. Well, I will wait to make the comment until we go to that example. So, just as a comment, okay, this is useful in economic analysis. And we will do two computations related to this model. So the first one is that we're given actual specific numbers for the constants, A, alpha, and beta. So Q of K and L is equal to 60 times K to the 1/3 times L to the 2/3. Okay? So one thing to notice is that actually 1/3 plus 2/3 is equal to 1. So we are satisfying our constraint. So we just made A equal to 60. Alpha equal to 1/3, beta equal to 2/3. Okay? And it follows the constraint that we have assumed. There are some details though about the units. So for K, it is the capital investment, but it is measured in units of $1,000. And L, which is the size of the labor force, it's measured in terms of worker hours. So, just as the choice of units might be important, since we might get some information later on. So the first exercise is to compute the output if the capital investment is 5,112 and then 1,000, and then you have 1,000 worker hours of labor force. So part of the first problem is to convert this in the units that you have, right? So because the units of K were in units of thousands, K is equal to 512 in terms of these units, and L, well, they were measured in worker hours, so this is just 1,000. You need the right units in order to not have a mistake in the computation. The second will be, so we might need some info, so I'm going to keep this one. To evaluate this function for the given values, Q of 512, 1,000, which basically Q of K and L, so you just plug in and have 60 times the K, which is 512 to the 1/3, times 1,000 to the 2/3. There are two observations that might make the problem a little bit simpler, which is that if you compute 8 cubed, that gives you 512. If you have, well, this is 10 to the 3rd power, but then you have it to the 2/3, right? So this would be 10 squared. So you can do the computation, and then you can take the cubic root, and you're done. So basically, this would be 60, 10 times 8 because of this. And then doing this computation, you would have 10 squared, which is 100. So if you do it, basically, okay, you have 48, okay, 48, 0, 0. So 60 times 8 times 100. And I have already made the comment that 1/3 plus 2/3 is equal to 1. That will be important for the next part of the exercise, because the second part asks us to show that output in part A will double if both the capital investment and the size of the labor force are doubled. So now you will see why this constraint of the exponents that their addition should give you 1. I have done a couple things in the development of previous examples, and the current one a little bit different from the textbook. In particular for this one I will do it, so just keep it an eye when you study for your exam. I do it differently in the hopes that it might be easier to understand. So this time I'm being a little bit more algebraic than numeric or doing the actual computation with the whole numbers, so just keep it in mind. Well, so in this case what you will do is a computation of the form, again, Q of K and L, where K now is twice 512 and L is 2 times 1000. So that should give you an idea of why we've wrote the double thing in this fashion. So Q at the point twice 512 and twice 1000. Of course I could write 2000s, but we're going to play with the powers a little bit and it will be more convenient to keep it just like this. So the rule is, again, whatever you have as a K, which is in this case 2 times 512, you elevate to the power 1/3, and whatever you have as the L, which is in this case 2 times 1000, you will take to the power 2/3, right? So the first thing that I can do is use lots of exponents, and this is 60 times 2 to the 1/3 times 2 to the 2/3, because I'm taking them out. Then I have 512 to the 1/3, 1000 to the 2/3, right? So I just factorize conveniently. Well, the second thing in factorizing conveniently is that I can put these two together, and this is 2 to the 1/3 plus 2/3. And then I can have this as 60 times 512 to the 1/3 times 1000 to the 2/3. Now, I know that the constraint is that 1/3 plus 2/3 is equal to 1. So that means that this is 2 to the 1 power, which is equal to 2. So now you see why we have this constraint. It's partly because of the observation in this part B. And if you think about it, this is basically Q, just comparing with the original rule that you had. Well, this is Q of 512, 1000. Okay? So what we did, basically due to the constraint, you have the factor of 2. Because the 2 powers, when you add them, they give you 1. If you have twice the K and twice the L, you will have twice the Q. That is why the constraint is important in this example. And doubling like the capital investment and the labor force, you will get twice the output, right? So that is the whole idea of this power law of this Cobb's whatever mode. So this is twice the previous computation, which was 48,000, which is 96,000, and we're done. But the whole value of this problem is to notice that because of the exponent rule that you have in this function of several variables, if you have a factor, which in this case is 2, you can do some manipulation so that you have the factor. If it was like 3 times each of the coordinates, you would have 3 times the factor, because you would have again the manipulation of exponents, and then you have 3 to the alpha plus beta, but alpha plus beta equal 1, so you have the factor. So that's the whole idea and value of this problem. But did you guys see how we manipulated it? Like, is it clear? Okay. So that is the worst of the problem, most probably. I do not work in this topic, so I cannot give you further insight on the application, but as a math person, it seems that the model is designed precisely to have that effect. That if you do an increase of both of the coordinates with the same factor, the function will also have that increase. So We continue now with a different application, but it is related to some previous examples we had observed, which is present value. So we saw a little bit of this before, but now we will see it with different kind of eyes. So the present value of B dollars in T years invested at the annual rate R compounded K times per year is, and then you have, there's a whole reason why this sentence is written in such a convoluted way, which is that it's trying to make evident how in the previous model that we studied there were several parameters, some of them assumed constant, but in this case they will be allowed to change. And if we allow them to change, we won't have just a function of a single variable, but of several variables. So if you actually include the parameters as variables, independent variables, then you have P, which is a function of B, of R, of K, and of T, as B times 1 plus R over K to the minus KT. So this is a function of 4 variables, like this present value computation. And there's an indication now of finding the present value of $10,000 in 5 years invested at a 6% annual rate per year, so annual rate compounded quarterly. So again, you have to be careful with the units. B, okay, 10,000. Yeah. Then you have R, the rate, which is 0.06, because you express this percentage just in decimal units. 6% per year. K is equal to 4 because you compound 4 times per year. And the time is equal to 5 years. So, okay, part 1. Part B, use the formula or the function. So P of B, which is 10,000. Don't confuse the commas of the number with the commas of the function input. So R is 0.06. Then K is equal to 4. And T is equal to 5. And you plug in each of the parts, right? So you have the B, which is 10,000. Then you have 1 plus R, which is the second, 0.06 over K, which is 4. Then this to the minus K, so minus 4 times the T, which is 5. Okay? Well, you would have a minus 20 over here, then you can do the division. If you introduce this in the calculator, this is 7,424.7. Which is approximately $7,425. So, again, part of the value of the problem is to make evident to you that you have actually studied objects mathematically, which can be understood as functions of several variables and not of a single value. Before, some of these parameters were assumed constant. If you do an evaluation for a given value, okay, that's the case. But in general, you can have a different annual rate, for example, right? Or a different amount of times when you compute. So, or of course, I mean, which was the original variable of interest, a different time of interest, maybe not in 5 years, but in 10 years. So, okay, we have studied at least something which has several variables before. And one of the last applications that we will notice is basically exponential population. So Is there a question? So far so good, is it clear? Yeah? Okay. So, look, we have seen the Malthusian model, or the Malthus model. Am I going too fast, or am I going okay? Is the speed okay? Or am I proving myself too fast for this? Okay. So look, try to look the Malthus model with different eyes, right? I mean, in the previous case, the only variable of interest was the time. In this case, what was assumed constant before, which if you think about it, okay, plug in the time t equals 0. Then this will be 1, and this will be up to 8. So A has the role of the initial population. K is a parameter that determines basically the rate of the growth of the population. And before, these were just assumed as constants. But mathematically, what you would say is that you're studying this in terms of a parameter space, where in addition of the time, you're adding the study of both parameters, the initial population, and the growth rate, because that might be useful eventually. Like, perhaps because the connection in this case is that you study populations of human people, and the math community is more familiar with populations of, say, appearing in math biology, right? But they see it with different tags in the sense that usually what you can prove with these models, not perhaps with the Malthus, but with something more complicated or such as the logistic, is basically the carrying capacity, or the population where you have, in a way, an equilibrium population. Like past that population, you might have a decrease in the rate of growth. So it is useful to study those parameter spaces because later on you can predict based on initial conditions or the value of the parameters the behavior. Not only perhaps what is the carrying capacity, but also if you have in more complicated models where there are mathematical models for the interaction of a predator and the prey in an ecosystem, etc., if there is a periodic evolution of the two populations, or if it's not, or if basically the predator eats so much the prey that it eventually just gets extincted. So that really depends on many parameters, which is the rate of growth of the populations and also the initial conditions. That's why it's worth to study this in a parameter space. Just because you might have equivalent troubles or problems when you study population of human people. Maybe you have a model of human interactions, right? Of, say, two, competing groups in terms of a given product, whatever, right? So the parameter space is worth to be studied. Now about making the whole list of what are the variables of interest. So P is the population at time t. A is the initial population, as I had mentioned. If you plug in t equal to 0, P is equal to A, so that has been cleared out for you. K is the relative, meaning per capita. Growth rate. If the population is currently 5 million people, there is an assumption in the units that is actually indicated in the solution, so just wait for me 1 second about that. And it's growing at a rate of 3% per year. What will the population be in 7 years? So before we go into the solution, there is an addendum, which is that the population P is measured in millions. It's not said in the statement, but it's clear in the solutions that that is an assumption. So you go to the solution, well, given the units, so you have p is equal to 5. Well, one of the variables is 5, and then the other, in terms of the rate, you have 3%, so that is 0.03. And then you have 7, which is the time. So the first is the initial population, which was 5 million people, remembering that the units of the population are measured in millions. So we're just going to evolve in time, which means using the formula that we have, which is plugging in like this, A times e to the kt. And so you have a equal to 5, e to the kt, so you have the product of 0.03 times 7. If you do the computation, basically you have 6.1684 millions. And yeah, I mean, just to make evident this, the initial population is 5 in million people, k is equal to 0.03, t is equal to 7 in years. The k is because you had a rate of 30% annually, and then the units of this are years, and this is in millions people. So this is million people. So, yeah, this should have been mentioned in the statement of the problem, not in the solution. But having said that, all the parameters has initial population currently, so we measure starting the time, so this is 5. Then we make the conversion of the percentage to the decimal, and then in 7 years, and we do the computation. Again, keep in mind, I mean, in math biology, you have more complicated population models, and where you might also model interactions between two different species. So just keep in mind that sometimes it might be worth to study the whole parameter space in addition to the variables of the actual population, because you might be able to prove theorems in terms of the behavior of the population. So it's not useless. That's all what I'm trying to say. So in terms of how to represent graphically this, what we have is the graph of a function of two variables, which is f of x and y. And this is important because, well, look, you might not realize it at this point, but there is a very big change in the job market where professions are getting more mathematical, and if you have such skills as data science and so on, you are a more competitive member. The point is that in that step of using data science, not only you have to do a preprocessing of the data, but also how you present your results might be useful. And that means that you have to do visualization. Usually, those parameter spaces are of way more variables than 3 or 4 variables. So the point is that it will be useful sometimes to look at the plot and how your function behaves. And then what you have is, for the plot, a set of all triples of the form x, y, and z, where you had a function of two variables, which was f of xy. However, xy is in the domain of f, and c will be the value of the function evaluated at x and y. So what you will do to represent this function of two variables is to plot it in a 3D space. You may have seen if you have used anything such as MATLAB or Python, etc. So what you have in that case is a 3-dimensional coordinate system. Where you have x, y, and z is representing x and y. Now, the clarification is that you add a third coordinate, which is the z-axis, which graphically is perpendicular to the xy plane. And the xy plane in the convention is taken horizontal, and the z-axis points up. So, if you want a graphical description of this, essentially this is what you have. You have the x, you have the y, and you have the z. I'm not sure if you have seen this or not sometime, but usually the way to represent the points in this xy space is basically like this. And then you have the x coordinate, the y coordinate, and the z coordinate. So try to study this. We'll continue from this point, and good luck.